Thanks, Martin, for the nice introduction, and thanks to the organizer for inviting me here. When they invited me, they asked me to do a bit of a link between the two parts of the conference. So you had a lot of X-ray imaging, so let's say high energy stuff, and then we'll have a few talks on lower energy stuff. So they asked me to do a bit in between in half an hour. That's easy task. And that is made even more complicated by the fact that the last 3 minutes from Bijou were very close to a lot of things I had to say. So I will expand on your nice presentation, on the end of your nice presentation. So I had to select some topics. Of course, in half an hour, you can't talk about all CMOS word. So I chose a few topics which are at the heart of a lot of X-ray imaging, as we heard before. So I will talk briefly about yield, radiation hardness, then about radiation hardness, dynamic range, speed, and then coming to the conclusions. And before the conclusion, I will have a few videos just to light up the talk. So first of all, you're just going very basically. So Moore's law, why CMOS is so powerful, because it has been we have more and more transistors. It has been going on for decades. And we have now transistors which are very small, approaching physical limit. And actually, that's a slide from, so the industry meets every couple of years to look at what they can do. And last roadmap of the industry actually said we can make transistors physically smaller. So if we want to continue, let's say, scaling and putting more transistor in a piece of silicon, then we have to go 3D, and then so we have the end of 2D scaling and the beginning of 3D scaling, but you will be, so even the transistor are a few nanometers, you will be hearing about nodes which are 1.5 nanometers or something like this. So how the Moore's law benefited the industry is in providing basically the base for pixel scaling, and that's a graph which is adapted from it was something which was first noticed by Eric Fossum almost 20 years ago now, that the minimum size of the pixel you can make is basically between 10 and 20 times the smallest transistor you can make. So nowadays, you can do even smaller we could do even smaller with 1 micron, but effectively people realize that about 1 micron is, there's not many image sensors go beyond 1 micron, and for example, mobile phone image sensors are now getting a bit higher up in pitch, in some cases. So that's where we come from. So a lot of, you can do very small pixels. And iPhone 7 is 1.12 micron pixel, 1.2 micron pixel. And for X-ray imaging, for example, we have very large pixels. So you can put something like 1680 pixels in one 50 micron, which is 50 micron in X-ray imaging world is a small pixel. Yeah. So, and how many pixels do you need to make an iPhone sensor? Only 7,000. So it's really a totally different world. And so when we start talking about yield or what to do with the pixels, then it's a kind of problem for designers. Well, there's a lot to do. We can do a lot, but what to do exactly? And designers have everybody has got a horror vacui, so we don't like empty spaces, so we want to do something. So we'll try to do something with this. The other considerations is that large pixels, so making large pixels is not just only putting things in the pixel. There are also other considerations, and one has to different trade-offs for noise and charge collection in the pixel. So there are some careful design which is a bit different from a small pixel where the light is collected immediately. So it's 1 micron diffusion or drift there, and it's collected. In a large pixel, if you do a very small diode, well, the light, not the light, but the charge has to travel a lot in the silicon, so there could be other effects related to this. And complex pixel, of course, in CMOS is not complicated. Even you can do it in active pixel sensor. There are other complications. Maybe I don't want to enter into this, but it is possible to do complicated electronics with high quantum efficiency in CMOS, and that's one of the design I did in my past work at Rutherford Laboratory. So that's a pixel which is very much like a hybrid pixel for those of you who know. And it has about 600 transistors in 70 micron pitch. Just one word about stitching. Probably all of you know about stitching, but stitching is, so you have a reticle and it's a different design style. So the full sensor doesn't fit in the reticle, so you have to do modules on the reticle, and then you build the sensor from modules. And in this way, we can get a very large, up to a wafer scale sensor. So the limit is just the size of the wafer. So I want to try to say a few words about yield for wafer scale sensor, because it's a different word, again, from the main market for IMASENS, which is fairly small. If you have a normal, so this represents an 8-inch, well, a silicon wafer, a CMOS wafer. Normally you have a lot of dies, and if you have one defect, is one die that dies, so that's not a big problem. It's only 99%, well, still 99% yield, something like this. But if you have a wafer scale sensor, that can be a big problem. You potentially can kill the sensor. This said, there are also some advantage in doing a wafer, an imager in general. It has got some redundancy built in the sense if you lose a pixel, it's not the end of the world normally. And then you can build redundancy in the electronics as well. But all of this to say that it's a different word, and effectively models which were developed for industry for calculating yield of dies, they don't work for large dies, and this actually, as far as I know, is a good thing, because the yield predicted by this model is 0, so that's not the case. So it's a good thing. So just trying to say something more about how to design or what the impact of defects can be on a wafer scale sensor. So that's a typical floor plan for a 3-side battable sensor, so that's already something a bit unusual with respect to normal imagers where you have all the 4 sides, you can put electronics drivers, but in a 3-side battable, you only have one side, and the other actually, you have to be careful also how you dice for when you go to the edge of the wafer. But so in a 3-side battable sensor, you see, most of the area, normally it's most of the area which is taken by the pixel array, and there is already probably some addressing logic, so it's not just pixels, there will be some driving electronics in the pixel array to do part of the, what would be the row addressing, if you think the row in my picture vertical. And then on the side where we can, where we have freedom, then we have the normal amplifier, column amplifiers, analog to digital converter, row address, and then other blocks, whatever we want to do with the CMOS itself. So there are 2 very distinct areas in the floor plan. So there's a pixel array, which is a huge area, which tends to be fairly empty, but it is huge, and you have very long lines to connect the pixels. And when I say very long lines, it's centimeters, 10 centimeters, 12 centimeters, or even more. And then we have a different area, which tend to be much smaller, but also much denser, because you have all the electronics is there, so you have to pack it somewhere. So if you look at defect types, when we analyze a defect and when we design a sensor, we have to look at different defect types, and I try to do a very rough classification. So as I said before, there are 2 areas, the pixel array and the periphery. And then we can look at I try to distinguish between localized defects, so where you have just a device failure or pixel internal routing failure, for example, and then global defects where you have long lines which are broken and you have shorts and opens. And then in the 4 boxes there, you have the effects of what they can do. So if you have a localized defect in a pixel, there's not, it can be very easy. I mean, it brings to the pixel failure, so it's not catastrophic for the sensor. And if you want to avoid that the pixel, maybe you get shorts between power supplies and ground, and then there is where the design has to help in avoiding these catastrophic failures. And then well, if you go down, of course, if you have let's say shorts, then you can lose columns or rows, so lines in general, and then sometimes you can also lose stitching blocks, and that can be a problem. In the periphery, if you have localized defects, in that case, because there are some lines driving for control of the sensor, you can end up losing lines, or while you're losing the sensor eventually, or having loss of functionality, and similar. And for global defects, again, you can lose lines and stitching blocks. So just closing this session about yield, I try to summarize in a very succinct way, but take-home message is that large pixels or large sensor demanded a very different design style. And one question, which is kind of piggyback on what Biju was saying before, is one thing we want to do is to harness the complexity and so put complexity in large pixels. So the second section was, if you remember, on radiation hardness. So I have just a very brief reminder of what the effects of radiation damage are on a CMOS sensor, and then come to the conclusion, say where we are in terms of how much radiation hardness can be achieved with state-of-art components. So I want to distinguish between what I call the CMOS is the electronics reading out all the transistors effectively, and ADCs, other blocks, other functional blocks one can have in a sensor, and then the sensor itself, and both would have 2 different types of damage. One which is called total ionizing dose, so a particle coming through generates electron-hole pairs, and then we'll talk later what they do. And the other one is what is called non-ionizing energy loss. So you get so particles are not generating particles are hitting atoms and moving them out of the lattice, so creating real defects in the silicon. So basically breaking the crystalline structure of the material. And on the side of these ones, there are also single event effects. So one particle causing, for example, a memory to flip, or big current to flow in the circuit when you have a latch up. I won't say much about those. But I just wanted to mention for completeness. So first part, so now let's look at the damage for CMOS. So if you have a photon, X-ray photon, or a particle coming through, or any ionizing radiation effectively generates electron-hole pair in silicon, and then they would be separated. And here you see the structure which is shown here is the gate, basically polysilicon gate, silicon dioxide and silicon. And at the end, you basically left with positive charge, which is trapped normally close to the interface. And so you have you start with the oxide or the transistor, which was neutral, and then at the end you have something which is positive, and that causes the transistor to change behavior. And this is kind of summarized, well, maybe that very technical slide, but so that's summarized by a quantity, which is the voltage, threshold voltage shift, which increases with the radiation. There is one good thing about going smaller in CMOS, something which was realized already basically over 30 years ago. So this picture is from a paper from 1980. So this represents how much damage basically we have as a function of the size of the transistor, simplifying. And you can see that as you make transistors smaller, the damage goes down, good thing, and even it goes down even more quickly when you go to very small transistors. So using very small technology is a good thing and kind of cure the radiation hardness, at least for, so I say the small feature size technology become kind of inherently radiation hard. Up to a point, in the sense that transistors are complicated structure and they have so as I said before, there is a part of the oxide there, but also we have to connect the transistors, and then when they connect, you go immediately on very thick, it's like having a big transistor, the equivalent of having a big transistor next to a small one. So you have to take care of these big transistors, and then people do funny things like round layouts, and in this way you can really take care of the radiation hardness of transistors. So there are ways, both through technology and through design, to get very rad-hard sensors. And I mean, in the past I worked a lot in particle physics, which probably delivers the worst type of environment available on Earth, and in space a lot. And there are really, people can make detectors or can make readout electronics in CMOS for these type of environments. There is, if you remember in my 4 boxes, there was one box for non-ionizing damage. I won't say anything on non-ionizing damage for CMOS, because effectively it's found to be immune, basically. So there's no need to look into these things. And so if you go to the sensor part, again, for ionizing those, there are some effect, maybe without going too much into the details, but basically they can be cured, or these rounds should have been there, it moved, but you can kind of see these. This is a diode design, in a rad-hard design, and it has similar shape of the transistors I showed you before, and that can cure the radiation hardness of the sensor. So that's for the ionizing dose. For the non-ionizing dose, so as I said before, so non-ionizing dose is a particle arriving, photon or a particle, and hitting an atom and displacing it and creating basically damage to the crystalline lattice. So it's really breaking the silicon or any other material. And I want to let's say, be a bit technical on this one. So this is a plot showing, again, it's non-ionizing damage as a function of the energy, basically, of the particles. And you can see there protons. So, for example, well, Phil is not here today, but we had a talk yesterday about proton therapy. So for when designing a sensor for proton therapy, one has to take care of this, because protons do damage to the crystalline lattice, so one has to think about this. Electrons do the same. Good news about photons for X-ray imaging is that there is a threshold at 250 keV, so most applications don't need to worry about lattice damage caused by the X-rays. It's only if you go to a radiotherapy application, then you have these type of photons. But so we have to take care of this type of damage, and what do we want to do So what happens to the silicon, and how can we basically cure somehow manage this damage? One thing, important thing, is that when the silicon gets damaged, the electron hole carriers, they get trapped more quickly. With increasing damage, they get trapped more and more quickly. So the solution is to try to get them to the right place before they get trapped, basically. And this means for the silicon device means collecting the charge very quickly, and the way to do it is putting electric field, which is not commonly there in an image sensor, not everywhere at least. So the solution to this problem is to use fully depleted CMOS. Normally, CMOS sensors are not fully depleted. They have a very big area which is not depleted. And in this field, there are different solutions which are starting to come alive. And one of them is, which comes again from the particle physics communities, to use high voltage process for the CMOS part. So summarizing this rather technical part, take-home message is, I summarized my take-home message in this table, which shows kind of limit, try to get the highest number possible where we can go with either bits. So for TID in both CMOS and the sensor, we can probably get to 10 megagray. So 10 megagray is 1 gigarad. There are some recent data about this. For the NEAL part, CMOS is, as I said, is very high. I couldn't really find a number. But for the sensor part, people are working in particle physics, for example, towards getting the number to 10 to the 14, 10 to the 15 neutron equivalent, which is a very high number. So just to give an idea, space is more like 10 to the 11, mostly applications. So there we're talking 3 orders of magnitude more. I have to say this number should be taken with a pinch of salt, in the sense that definition of what is acceptable in a sensor used in a radiation hard environment depends on the application, and people might adjust the specs so that the sensor can live longer, or in some application is not needed really. So third part, how many minutes? Probably I should, how many minutes, Martin, do you know? 5 minutes. That's what I thought, yeah. So I will be very quick on this part. That's a 3-minute syndrome. So high dynamic range, there are different solutions. Also, Biju mentioned some of them. The one I probably like most is, there's dual gain pixels, but also lateral overflow can deliver linear pixels which have a very high dynamic range. And this is an example, again, taken from one of my last projects I was working on in my previous life. So that's the Percival project. And there we achieved a dynamic range of 20 bits on a 25 micron pitch. The advantage of the lateral overflow is that you don't need to have any pre-knowledge of the image you want to acquire, like what you need for dual gain, for example. And of course, photon counting is, for example, a way of extending dynamic range even further and maybe providing even more things like color imaging. Ideally, photon counting gives you no noise. And these are different solutions found in literature, but what I want to show is that this is a 55 micron pixel in one of the latest Medipix chip by CERN. And you can see there's a lot of electronics to do this photon counting. There are some other solutions which people are trying to make live. So do photon counting with much lower count, transistor count. Still more than 3, but lower count. And one thing I want to mention also is that noise in CMOS image sensor is becoming very good. And this is a slide. These are slides from a Cavaito paper and one recent paper from Eric Fossum. And you can see the noise going down, and now we are sub-electron noise. So we start doing photon counting with conventional image sensors. And that's maybe something to bear in mind. The performance in CMOS sensors have changed, so maybe there are also some changes which can be done in sensor for X-ray imaging. That was my take-home message. And last point was speed before going to the conclusion. And I will skip through the technical bits and just show a couple of plots. So this is shows speed of pixels or CMOS sensor as a function of the ear. And the speed is labeled with a pixel rate. So bear in mind the gigapixel. So this is the line, for example, for a gigapixel per second, which means you can read a million megapixel sensor at 1,000 frames per second. So that's high speed. And nowadays, fastest sensor, which are, by the way, megapixel sensor, they go at about 20,000 frames per second. But they are smaller sensor than a wafer-scale. They're not wafer-scale. They're relatively large, but not wafer-scale or not stitched at all. So if we go to wafer-scale, the frame rate becomes a bit smaller. And this is a slide with axes just for sake of confusion. They are different from the previous one. So that's a megapixel in one direction and frames per second in this one. So the now, in the plot before, I had gigapixel rate, constant gigapixel rate was horizontal. Now it's this 45-degree line. And these are most, if not all, of the wafer-scale sensor in the field. And you can see where they stand, and they are slower than the other ones. And these are the sensor which is commercialized by VivaMOS, which I designed when I was in RAL, which is one of the fastest in the field, providing 30 frames per second at almost 7 megapixel resolution. And so the take-home message is that, the pixel rate for X-ray images is increasing, and we have the potential to go even further when we look at smaller chips, and what can we do with this? So that's a question for the users. And the very last section, I got 1 minute, maybe?
Yeah.
Already gone. Already gone.
1 minute.
Below, okay, but these are just videos, so we can think about questions already. And this is so the panel I was showing before. This is a two-side battable panel with 50 micron pitch, and that's a movie from the very first example. So what I showed there is the optical equivalent taken at normal speed. So you can see the X-ray is taking pictures at video rate. And just to show, that's another part of a medical, just going towards the next talk somehow. Different sensors, that's a high speed, the very high speed sensor I designed. So this goes 2 million frames per second, and it's used to study particles for dental etching. And this is another interesting application, which is more related to the cancer care topic we have in this workshop. So this video was taken at 5 million frames per second, and it shows micro bubbles bursting and spilling out drugs. This is in a test, but the idea is that then you can use this to provide localized injection of drugs to cancer cells. And then coming to the conclusion, so I think it's a bit what also Biju was saying. So CMOS technology can offer improved performance, and so far what we've seen in the X-ray medical field is probably mainly a kind of replacement of existing panels, but CMOS can offer much more. So it'd be good to see if we can do something with that. And there have been, in recent years, improvements in dynamic range, radiation hardness, and speed. And we want to look into harnessing complexity and putting more complexity in pixels while making a viable product for the field. That concludes my talk, so thank you for your attention.